Oh, got it. So can you see the screen?
Yes, can you please put it in the presentation mode just to check quickly?
Okay.
Yeah, it's perfect. So hello everybody. Today I have the great pleasure of introducing Professor Dong. He is our last Can't Around the World speaker. Professor Dong is a full professor at the School of Transportation, Science and Engineering at Harbin Institute of Technology. He received his undergrad, his master's, and his PhD from the same institution. Some of his research interests include full-scale pavement testing, pavement dynamic mechanics, and innovative and sustainable pavement materials. Today, he'll be discussing a very nice topic, which is the dynamic response of asphalt pavement under two different perspectives. The first perspective is looking at it from a theoretical and modeling perspective, and the other one is using some full-scale analysis. The presentation will be for 40 minutes, followed by 20 minutes for discussions. So please, if you have any question, do not interrupt the speaker. Raise your hand virtually at the end of the lesson or the lecture, sorry. Or you can also write your question in the chat section, and I'll ask it on your behalf at the end of the lecture. Please join me in welcoming Professor Dong.
Thank you. Thank you very much for the invitation. So I will start. Good evening, everyone. Actually, this is the morning here, but I'm Zhe Dong from Harbin Institute of Technology. Actually, I spent 1 year in UI at 2011, and I experienced and learned a lot there, which gave me a lot of wonderful memory there. So special appreciation is given to Professor Imad Arkadi. Thank you very much for the hosting me. And as for the lecture, I would like to introduce the research work I have been working on for more than 10 years. Dynamic response of asphalt pavement from analytical solution to field monitoring. Before that, I would like to introduce our university and school with several slides briefly. Following that, I will introduce the three aspects of dynamic response of asphalt pavements: analytical solution, finite element simulation, field monitoring, respectively. So Harbin Institute of Technology, HIT, is affiliated with the Ministry of Industry and Information Technology of China, which is focusing on the engineering discipline. HIT is also listed as one of the top 9 universities in China. Here we have 3,850 full professors, full-time faculties, and together with nearly 50,000 students. Our university has 3 campuses. From the northern to the southern China, Harbin main campus with all disciplines, where the Weihai campus specialized in the automotive engineering. Shenzhen campus in the South China is a newly built one, which is more similar with the system of Euro-American university. So the HIT is well known as the space engineering, and quite a few, the first of China, were born here. Generally, our university is committed to focus on aerospace industry, serve in national defense, and contribute to national economy. As for the School of Transportation Science and Engineering, where I'm employed, there are 71 faculties in total. Among them, there are 20 full professors and 24 PhD supervisors. 5 departments in our school: highway and railway engineering, bridge and tunnel engineering, road material engineering, transportation engineering, and transportation information and control engineering. There are 6 named professors selected into National Talent Program in total. Different from the Department of Civil Engineering in US University, we have 5 schools to support 1 civil engineering discipline in HIT, including civil engineering, transportation engineering, municipal engineering, environmental engineering, and architecture engineering. This is kind of a little bit different from the UI. Some professors in UI, like Professor Imad, of course, Professor Rosler, Professor Tutumula, or Professor Yan Feng, may have some impressions of our old building as they visit us before. Well, in the last 3 years, school facilities have improved a lot. We have a second building, Building B, in service for 2 transportation-related departments, while the third building specialized for the innovative research of transportation, future transportation, will be put in use in 2022. It will support 5 international research centers: smart transportation, big data in transportation, transportation infrastructure, intelligent decision, sustainable development of transportation infrastructure, and regional collaboration of integrated transportation. And welcome you guys to come here when the 3 buildings are put in use. Okay, so let's get back to the technical part. When we are talking about the structure, design, or performance evaluation of pavement, we have to provide some necessary information like material properties, environmental factors, vehicle loadings, and the structure conditions. No matter which way we use, theoretical derivation, numerical simulation, or field measurement, we need to get the dynamic response to reflect the mechanical behavior of asphalt pavement, like stress or strain or deflection. Then we could evaluate or predict the performance, the service performance of asphalt pavement, like rutting, low temperature cracking, fatigue cracking, or reflective cracking. As you can see in the framework, that among all these dynamic responses of asphalt pavement are the primary parameters we need. Well, we do have some challenges when we want to get them. The first one is highly complicated environment. The large temperature range exists from the winter to the summer, or even in one day at some province of China. The temperature, moisture, and the radiation are changing every hours. However, their effects are difficult to quantify. The second is poor loading representing. The real traffic vehicle load is insufficient to be simplified with uniform static loading. The structure design parameters are seldom rechecked during or after construction except deflection. Another challenge, I think, is most of the performance evaluation rely on the visualization of pavement surface, which is kind of post-detection and evaluation. All these factors mentioned here should be expressed with the input parameters, like in form of time dependent, temperature dependent, stress dependent, moisture dependent in the material properties. As a result, research efforts we are employed in this part dynamic response of asphalt pavement is divided into three aspects. Analytical.
Professor or Isaac, I think we lost.
Yeah, Professor, we cannot hear you. I was just making sure that I'm not the only one who's not able to hear him. Professor Dong, can you hear me? I think we lost you.
Is he still on the call? I think he is. Right?
Yeah, I can hear
Yeah.
his voice, but it seems that there is an internet issue. Professor Dong, can you hear me? I see you're still connected. I can see that you are talking, but we cannot hear what you're saying. We still can't hear you.
You may want to send him an email, Isaac.
Yes, I'm doing that right now. He can hear us, but we cannot hear him. Professor Dong, if you hear me, can you please exit and re-enter?
see. I think how Wang is on the call, so maybe he can send him a message with WeChat.
Hi, Professor. I just did.
Yep, that's what I was thinking. Thank you.
Yeah, but I hope he look at it. So
Yeah, I hope so too.
Yeah, me too. I also sent some message via WeChat to Professor Dong,
Yeah.
but probably he's busy.
Let's see.
So he sent now a message in the chat saying he needs a few minutes. He's checking what's going on.
How are you, Ima?
Professor Akadi, I think you're muted right now.
yeah, you muted, Professor.
Yes, now I see your face. How are you, Limping?
Good, good, thanks. I already sent Don, a message. I called him, but probably he's using the line. Looks like he's back.
Yeah, I'm sure.
Ma, you look, so energetic today.
Oh, come on.
Over energy. Yeah. I think I have to probably turn this one. It's too much, kind of.
Yeah, now there's an issue in using Zoom, I think, in China.
Yeah.
Even I don't think they can log in. I think Professor Dong probably use some other ways. Otherwise, I don't think it's working even now.
Wow.
Zoom should be okay, right? Zoom.
We tried it yesterday. It was working perfectly.
Should be okay.
Hi, hello, everyone. Can you hear me?
We can.
You can hear me,
Yes.
Professor?
Yes.
Yep.
Oh,
Great.
sorry.
That's okay.
I have to change another. Okay, maybe I have to stop the video so that the internet.
Yes.
Yeah,
that's
you can do that.
Yeah.
Yeah.
Please do
You're
that.
a co-host now. You can start sharing your screen.
Yeah, I can share my screen right now.
And please, everyone, if you can mute yourself and also turn off your video, this might help. Thank you, everyone, for your patience.
Okay, so can we continue?
Yeah, I can hear you.
Okay. So the first part, sorry for this. Maybe the internet is not good here. The first part is analytical solution. Firstly, I would like to start with the basic principles. Different from numerical simulations, which could consider very complicated loadings or boundary conditions, we have to make some simplification in order to get analytical solution, which has high efficiency compared with finite element simulation. General framework for solution is beginning with the basic equations. We have to do some integral transform for like the Hanker transform, Fourier transform, Laplace transform to make the solution to be solved in frequency domain. Then introducing the loading conditions or boundary conditions by utilizing the transfer matrix method or wave propagation approach. We could then derive the solution of a multi-layered pavement system. After the numerical inversion, we could eventually get the results. So what kinds of cases can we consider by analytical solution? At present, our developed analytical solution program could consider various loading types, such as static loading, which is commonly adopted in the specification of pavement structure design in China. Impulse load for the application of falling weight deflectometer test, moving load with 3 directional non-uniform contact stresses, and moving dynamic loads induced by the unevenness of pavement surface. As for the material properties, elasticity, visco elasticity of asphalt layers, transverse isotropy due to pavement compaction, saturated or unsaturated porous medium, considering the existence of moisture, and modulus gradient induced by temperature field or aging effect could be considered. For the boundary condition, full boundary bonding, full sliding, or imperfect bonding could be taken into account with the use of Goodman model. This slide is to illustrate to the advantage of analytical solution, taking the multi-layered pavement structure subjected to non-uniform moving load as an example. The proposed analytical solution has a better effectiveness, a lower computing cost, and easy to input. I will introduce some typical applications in the following slides. Asphalt pavement design considering non-uniform moving load. In the conventional pavement design, vehicle loading is always assumed to be a circular uniform static load. The developed solution or program here could consider irregular tire imprint or and moving states by superpositioning some small rectangular moving units. The second application is considering surface unevenness, moving dynamic load. In this case, vehicle dynamics and pavement dynamics are reflected by the changing amplitudes of moving load due to the road unevenness. Taking a culture model of truck as an example, the left figure shows here the time history of longitudinal strains at the bottom of asphalt layers along the driving directions. The peak of strain fluctuates due to the moving dynamic loads. The effect of unevenness and moving speed on the strains could be also discussed. High unevenness significantly results in a large pavement response, while high moving speed leads to a lower response. Besides, the effects of stiffness and damping of suspension or tire could also be analyzed. High suspension, as we can see from the figures, high suspension damping and low suspension or tire stiffness could lead to a lower responses. In contrast, the tire damping almost have no effect on pavement response. The third typical application is quantifying temperature or aging effect along pavement depths. Generally, the temperature or aging results in the modulus gradient along pavement structure. In the conventional solution, this could be achieved by citing more divisions of layers, we call it sublayers, with a constant modulus, while the proposed analytical solution can consider the modulus varied exponentially along the depths. Therefore, we could use fewer sublayers. This feature contribute to a great improvement of efficiency. Another application is the interpretation of moisture damage for asphalt pavement. One of the primary reasons for moisture damage is the repeated water scouring within the asphalt layers. Based on the theory of porous medium, the pore pressure in asphalt pavement under impact load could be obtained. It can be observed that the higher pore pressure accumulates within the middle asphalt layers, which is consistent with the results from the field coring. So in the second part, I would like to talk about the finite element simulation of asphalt pavement under accurate tire loading. The reason for this is we utilize the assumed loading patterns in the previous part, that is the analytical solution part. As a result, the most important thing is to find a more accurate tire loading by laboratory test. Unlike the simplified loading distribution employed in analytical solution, the real traffic loading is very complicated due to the interaction between the tire and the pavement. Some factors we have to consider: the changing contact areas, even for one tire on different pavement surface, the three-directional non-uniform distribution, and the variable loading speed caused by the real-time traffic conditioning. But it is almost impossible to measure three-directional contact stress in actual running states accurately. The framework here is first measure the static vertical contact stress of truck or aircraft in lab. And the second, carry out the tire simulation with the same tire parameters. Then calibrate the finite element model with the previous measurement. Third, utilizing the calibrated model parameters to simulate different running states, including static, rolling, braking, and pulling. In this way, we could establish a comparatively accurate contact pressure database for different tires. We could call this as a digital loading model database. So to achieve this objective, we developed a static loading system for tires specially. Different axle load ranging from 0 to 25 tons could be applied on different types of tire. Also, different tire inflations could be tested. Based on the loading system and the text scan pressure system, the tire contact pressure with a desirable resolution can be easily achieved. Subsequently, we compiled a specialized program to deal with the obtained data. Geometric and mechanical parameters for characterizing tire contact pressure can be automatically calculated, like area, shape, length, and hardness. Here are some results for contact stress measurement. This plot presents the vertical contact pressure with the tire inflation of 0.83 megapascal. The shape of tire imprint or grinding pressure changes from an ellipse to a drop with the increase of axial loads. The second plot gives the vertical contact pressure with the axial load of 33.5 kilonewton. The shape of grinding pressure shows a transition from a butterfly to a rectangular and finally to a drum with the increase of tire inflation pressures. Besides, it was observed that from the figures that the axial load has an apparent effect on pressure in shoulder, while the tire inflation has an obvious effect on pressure in center. This slide presents the static tire simulation results by within the Abacus platform. We could acquire a series parameters like contact pressure, tire imprint, just mentioned before. This is the comparison between the measurement and the simulation. And this is the verification of inflatable deformation. And this is the verification of radial stiffness. By comparing the measurement and the simulation results, we could conclude that the established of tire model was satisfied with the requirement. Consequently, we can use this model to implement it, more simulations. So based on the calibrated tire model, we carry out further finite element simulation, including braking, rolling, and pulling within the Abacus platform. This slide takes one light truck as an example. The effect of different running states on contact stress distribution could be observed here. The main difference among these three states is the longitudinal stress. Its peak value appears at the back of moving direction, while its direction are reversed between traction and braking condition. However, in rolling conditions, the longitudinal stress values are very small and could be neglected. In contrast, the running states has a little effect on distribution and magnitudes for vertical or transverse contact stress. So after getting three directional moving loads as input, we could eventually calculate dynamic responses of asphalt pavement by finite element simulation. The top right is one typical pavement structure in China we adopted. We have three asphalt layers and two semi-rigid base courses. The moving load could be implemented with deload or ultraload subroutines within the Abacus platform. The physical elasticity of asphalt layers was extracted from the dynamic modulus test of asphalt mixtures and transferred into Prony series by fitting the master curves of dynamic modulus. This slide is used to illustrate the effect of horizontal stress loading on dynamic response of movement. Three cases were compared here. Three directional loading in the light blue line, and the horizontal loading in red line, and the vertical loading in purple line in each figure. The observing point was selected at the top surface layer, right under the tire center line. time history of stress and strain in 3 directions were presented here. From the results, we can find that the existence of horizontal loading has a great strain histories. To be specific, for this case, the peak values of longitudinal and transverse stress reduced around 10%, while the strain increased around 20 to 30%. But when we analyze the searing stress and strain, we can observe that the peak values in all 3 directions are influenced significantly, which means the existence of horizontal contact stress cannot be ignored in the calculation. This could be used to explain the failure or top-down cracking mechanism in some situations. So in the part 3, I would like to talk about real-time response monitoring of asphalt pavement by FBG sensing technology. Here, I want to introduce 3 aspects. So why real-time response monitoring is so important and why we use FBG sensing technology. The performance of asphalt pavement gradually deteriorates under repeated traffic loads and natural environment. Post-evaluation methodologies such as microscopic surface survey or external non-destructive tests are commonly used in pavement engineering. However, pavement structure is more like a black box. Current testing means cannot obtain the internal conditions, especially stress or strain information. And these parameters are important in structure design. As a result, we cannot realize a real-time pavement performance evaluation accurately. Therefore, the pavement health monitoring, like the structural health monitoring using built-in sensors, could be applied instead of the method mentioned before. To conduct pavement response monitoring, the use of durable and high precision sensors is premise. The fiber grating sensors meet our needs. Actually, in the past 10 years, our group has developed a series pavement used sensor based on the principle of FBG sensing technology. This is a typical pavement response monitoring and analysis system we established before, which consists of security module, environment module, loading module, and dynamic response unit. This system was established primarily based on various types of FBG sensors, except the weight in motion. So accurately obtaining the pavement response is extremely important for subsequent performance evaluation, while the unbanded sensor will definitely cause the interference to the measured pavement material. The coordinated deformation mechanism between pavement material and the unbanded sensors is necessary to be discussed. The geometry and modulus of sensor are optimized to reduce measurement variability through finite element analysis. Here, the results illustrate that the modulus of sensor sensor need to match that of measured material, and the sensor with 10 centimeters long and the anchor with 5 centimeters in diameter are proposed. In addition, we developed 3 calibration tests under different loading modes, including 4-point bonding beam test, uniaxial compression test, and the structural testing adapted from the wheel tracking test. In this way, we could validate the working performance of the developed sensors. We also try to develop some new types of sensors. For example, string sensors with different encapsulating materials, high modulus sensors with fiber FRP, fiber reinforced polymer packing could be used in concrete pavement, and the low modulus PP packing could be used in asphalt pavement because it's lower modulus. Another is the principal stress sensor we developed. It was designed theoretically to measure the principal stress at the proposed point. It was designed into spherical shape, utilizing 3D printing technology. Also, the interlayer displacement sensor, which was proposed to measure the slip between layers, especially for the road section with long and large vertical slope, was developed here, and also used the 3D printing technology. In the following slides, I would like to introduce some engineering applications of pavement response monitoring. This slide presents the system conducted in Beijing Capital International Airport. We put the system in one taxiway. The sensor layout consists of 3 units, namely response monitoring units, positioning identifying unit, and the temperature monitoring units. All these sensors are installed at the bottom of lower asphalt layers. The pavement structure in Beijing Airport is 2 asphalt layers, and the bottom is a concrete. So in this part, we developed 2 methods. One is the aircraft transverse wandering has a notable effect on dynamic response. Sensor closing to the aircraft loading presents higher amplitudes than others. The position identifying unit is employed to acquire the aircraft transverse offset through comparing the response peaks induced by the nose gear of aircraft among 7 transverse string sensors. Aircraft speed also has a significant influence on dynamic response. In this case, we used 2 sensors of the same type in the response unit, and the time difference could be calculated by this two response peaks, because the distance between the 2 layers is fixed and known, so we can get the moving speed. Another application is the back calculation of layer modulus. We develop an algorithm based on the response information obtained. To achieve this, we need the embedded pressure shells at the bottom of each layer, and 1 string sensor at the bottom of a surface layer. The back calculation consists of 2 steps. First, the modulus ratio of each layer is determined by matching the measured stress at the bottom of each layer and the corresponding calculated stress in 10. Then the modulus of a surface layer can be calculated by matching the measured and the calculated strain at the bottom of a surface layer. In this way, the module of each layer can be back calculated easily. Compared with the traditional modulus back calculation method, the proposed one is absolutely convergence and also can be conducted without any interruption to the real traffic. The second engineering application is accelerated loading test, collaborated with RIOH, a research institute of Highway Ministry of Transport. The primary purpose of this research is to determine the best asphalt mixture used in the rehabilitation project for Beijing China Avenue from 4 proposed asphalt mixtures. We were trying to minimize the permanent deformation of this avenue, especially for some special highway loading. In this project, we also developed a Rutting prediction model based on APT results. The Rutting prediction model integrated the measured strain from FBG sensor and non-linear viscoelastic model. In the proposed nonlinear viscoelastic constitutive model, the linear dashpot was replaced by nonlinear dashpot. As a result, it could be describe the third phase of permanent deformation in creep curve. The routing of asphalt pavement could be calculated with maximum vertical strain measurement, sublayer thickness, linear viscosity, and the traditional parameters in Burgess model. The accuracy of Rutting prediction model was acceptable for the proposed pavement structure validated in the APT test. The third
Professor Dong? Can anybody hear him?
I think we lost him again.
Yeah, we lost him.
I think he's trying to reconnect now. He left the... Professor Dong, can you hear me?
Can you hear me?
Yes, I can.
Okay, okay. The internet is so terrible. So I can start, I can now share the screen.
Yes,
Okay.
but
Got
please,
it.
if you can just focus on the remaining slides, because we need to stop at 8, which is in like 6 minutes.
Okay, okay. Okay, the third engineering application was implemented in Jilin province. This is the full pavement structures. We want to establish a long-term and a real-time monitoring system. This is the program we developed here. And in this project, we establish a fatigue prediction model, which combines the dynamic modulus, the measurement strain, and material parameters. So let's to sum up, the presentation here can be summarized into 3 aspects. Generally speaking, analytical derivation is the numerical and its numerical solution for dynamic response of asphalt pavement is more efficient in some specific and simple loading and boundary conditions compared with finite element simulation. And finite element simulation, considering paving interactions is a useful tool for us to know exact dynamic response of asphalt pavement, due to we can consider some complicated vertical vehicle tire patterns, and a real-time and long-term FBG sensor based monitoring system is applicable for pavement engineering. So for the future work, we want to establish a unified pavement design platform, and the programming is really important. And another one is to measure 3 directional contact stress with new developed equipment, because it is difficult to measure the 3 directional contact stress in the real moving state. Another is the distributed fiber monitoring technology. Compared with the traditional FBG monitoring technology, I think it is more promising and accurate and applicable. Thank you very much for your attention. I'm sorry for the internet. Actually, these days we could not use the Zoom. I think maybe it's the reason for the internet. And welcome you guys to come here, visit us in your convenient time. And by the way, representing our school, welcome PhD students in UI to join HIT after graduation. And nowadays we are recruiting faculties globally. So welcome any questions here or through the further contact. Thank you. Thank you very
so much, Professor Dong, for this very nice presentation. It was very informative. Unfortunately, due to the delay that we had with the problems, the technical problems with the internet, we will not be able to take questions. But if you guys have any question, I think you can email Professor Dong directly. He can, hopefully he will be able to answer most of them. This is our last Cant Around the World. Our journey around the world has come to an end, but hopefully in the fall we're gonna have another seminar, and we stay tuned for more information about the new seminar in the fall. Thank you so much, Professor Dong, for your time.
Thank you very much.
Thank you. We'll see you soon.
Thank you, Professor Iman, and see you soon.
Yep. Thanks.